Welcome to AI Paper Podcasts. Today we're diving into something pretty cool. How AI is turning, those sometimes messy 3D scans of rooms into interactive virtual worlds.
Exactly. It's about going beyond just a 3D picture.
Yeah, not just static images, but creating digital twins you can actually mess around with, simulate things in. It feels like a huge goal in the field, making these super realistic digital copies of everything.
It is, and the paper we're looking at, Literality, offers a really novel pipeline for this. It takes raw RGB-D scans, that's color and depth data from indoor scenes, and turns them into these compact, realistic, and crucially interactive 3D replicas.
Okay, interact is the key word there.
Definitely, because, traditional methods like Gaussian splatting are nerfs, and they give amazing visuals like 3D photos, but they're passive. You can't open a door, you can't pick anything up.
Right, they lack that underlying structure.
Exactly. Literality aims to build what they call graphics-ready scenes. So individual objects, articulation meaning parts that move, like drawers, high-quality PBR materials for realistic lighting, and actual physical properties.
So it looks real and behaves real. That sounds like a massive step. And they're getting good results.
State-of-the-art, actually, in some key areas. Like, their object retrieval doesn't need pre-training, which is neat, and they're really good at figuring out the materials, the textures, even from, tricky real-world scans.
Any applications? Where would we use this?
Oh, all over. Think much more immersive AR and VR, next-gen games with truly interactive environments, robotic simulations that are way closer to reality, and really functional digital twins for buildings or factories.
Okay, lots to unpack there. So let's dive deeper into how Literality actually pulls this off. All right, so let's get into it. You might be thinking, we already have pretty amazing 3D reconstruction, right? So what's the big hurdle Literality is tackling here?
That's a really good question because things like nerfs and Gaussian splatting are incredible for photorealism. They capture the look, the geometry, the texture fantastically well.
Yeah.
But the outputs are fundamentally passive. It's like a beautiful frozen moment in 3D. They don't have the semantic richness or the functional information you need to interact with the scene. You can't open a cupboard. You can't simulate physics.
Okay, so it's the difference between a picture of a switch and a switch you can actually flip in the virtual world.
Exactly. That's the core idea behind needing graphics-ready reconstruction. It's about making scenes ready for, like, a game engine or a simulator.
And what does graphics ready really mean in practice? What are the ingredients?
So a few key things. First, it needs to be object-centric. Each thing, a chair, a lamp, whatever, has to be recognized as its own separate entity you can potentially interact with, not just, a bunch of colored points.
Got it. Individual objects.
Second, object functionality. If something can move in the real world, like a door or a drawer, the model needs to capture that potential for movement, that articulation.
Okay, makes sense.
Third, PBR materials. Physically based rendering. This is crucial for making things look right under different lighting. If you change the lights in your virtual scene, the surfaces need to react realistically. Wood should look like wood, metal like metal.
Right, not just a flat texture.
Precisely. And finally, physical properties. Things like mass, friction, how something responds to gravity, collision information. You need all that for realistic interactions and simulations.
Wow, okay. That's a lot more than just geometry and color.
It really is, and it's different from some prior simulation work, things like AI2Theash or Proc2Ash. They often focus on generating lots of diverse scenes for training AI agents, sometimes sacrificing faithfulness to a specific real place. Literality is trying to get both high realism and interactivity directly from a scan of an actual room.
That does sound incredibly ambitious.
Yeah.
So how do they structure this? How do they break down this huge task?
Yeah, they have a clear plan. It's a 4-stage pipeline. Each stage tackles a specific part of the problem, building on the previous one. It's quite systematic.
Okay, stage 1. Where do they even start? With what I imagine is pretty messy scan data. How do they make sense of that initial chaos?
So the input is the RGB-D scan data, the color images plus depth for every pixel. They start by getting a basic understanding of the room. They use robust tools like Apple's Room Plan if it's an iPhone scan or other open source options. These give you the basic room layout, walls, floor, ceiling, and initial guesses for where objects might be, represented as oriented bounding boxes.
But you mentioned noise earlier. These initial detections aren't perfect, right?
Not at all. That's the noise problem. Real-world scans are messy. You get partial views, objects blocking each other. Maybe the lighting wasn't great. The person scanning moved a bit.
Right.
So the raw detections might have objects floating slightly or overlapping weirdly. Maybe walls have gaps. It just doesn't look physically right, and it would break any simulation.
So how do they clean that up? How do they impose some order?
This is where their core structure comes in. The scene graph. Think of it like a detailed blueprint plus a relationship map for the room.
Okay.
So you have nodes in this graph. These represent the key things: walls, windows, doors, the objects they detected. Each node has info, its position, size, orientation, and even cropped images of what it looks like.
And the relationships.
That's the edges connecting the nodes. These define how things relate spatially. Like this cabinet node is attached to that wall node. This vase node is on top of this table node. Maybe you have a table chair pair, or edges connecting adjacent parts of a larger object.
So it's encoding common sense about how rooms are arranged.
Exactly. And this graph structure isn't just descriptive, it lets them enforce constraints to make the layout physically plausible.
How do they enforce them? What if things are still overlapping after detection?
They use an iterative process called constraint-based collision resolution. It's pretty neat. Imagine tiny virtual forces gently pushing overlapping objects apart until they don't collide anymore.
Like a physics simulation itself.
Sort of, but guided by the scene graph constraints. For instance, if a picture frame is marked as attached to wall, the resolution process will only let it slide along the wall, not float off into the room or push through the wall. It intelligently resolves collisions based on the object's type and relationships.
Okay, that makes a lot of sense. You end up with a structured, physically plausible layout. So the room structure is sorted. What about filling it with the actual 3D objects? You can't just use placeholders, right?
Absolutely. Stage 2 is object reconstruction. And yeah, the goal is to find the best matching 3D model from a large database for each detected object in the scene. Not just any chair, but one that looks like the scanned chair and, importantly, has the right functionality if needed.
And how do they find the right one? Databases of 3D models are huge.
They are, and Literality uses a training-free retrieval approach here, which is a significant advantage.
What does training-free mean in this context?
It means the core retrieval mechanism doesn't rely on a deep learning model trained specifically for this retrieval task on this specific database. So if you add thousands of new 3D assets to your library tomorrow, you don't need to retrain the system. It can leverage them immediately. It makes the whole thing much more scalable and adaptable.
Okay, that's clever. So how does this training-free retrieval work?
It's a hierarchical retrieval process, multi-step, multimodal. It starts broad and gets progressively more specific.
Walk me through it.
Okay, first, semantic filtering. Based on the initial detection label, like chair, it narrows down the huge database to just chairs, or maybe even refines it further using attributes like armchair or office chair if the detection provides that.
Step 1, narrow the category.
Right. Step 2, image-based retrieval. They take the 2D image patches cropped from the input scan showing the object, and they compare these visually against pre-rendered images of the candidate 3D models. For this, they use a powerful vision encoder, Dino V2.
Kind of.
Yeah, it's really good at understanding visual similarity even across different viewpoints or styles. So Dino V2 helps find, say, the top 10 3D models that look most similar to the scanned object from the available views.
Okay, top 10 visual matches. Then what?
Step 3. Pose-aware rendering and comparison. This is crucial. They take those top 10 candidates, place them virtually into the reconstructed scene at the detected pose, position, and orientation, and then render new images from the exact same camera viewpoints as the original scan.
So you're comparing apples to apples view-wise.
Precisely. These newly rendered views are then compared again using the visual encoder. This really refines the match because it accounts for how the object looks in that specific spot with that specific lighting and angle in the scan. This might narrow it down to, say, the top 4 candidates.
Okay, getting closer. What's the final selection step?
Step 4, contextual selection. Here they bring in a large language model, like GPT-4o. It assesses the remaining candidates based on higher level stuff like style compatibility with the room, proportions, overall visual coherence. Does this ornate chair fit in this minimalist room? GPT-4o helps make that final judgment call to pick the single best match.
Wow, using an LLM for aesthetic and contextual fit. That's smart.
Yeah, it adds a layer of intelligence beyond just pixels. They also do smart clustering for identical objects. If there are 5 identical chairs, they retrieve them together. And their database is pretty big, over 5,000 assets from places like 3D Future, AI2 Theor, Sketchfab, aligned with common categories. And crucially, AI2 Theor provides articulation data, which is key for making things interactive later.
Okay, so now we have a structured room filled with the right high-quality 3D models correctly placed. But they probably look generic, right? Like default textures. How do they get the specific look of the scanned objects, the materials?
Right, that's stage 3, material painting. And you're spot on, getting the materials right, the specific wood grain, the fabric texture, the exact color from real-world scans is notoriously hard.
Why is it so difficult?
Well, several reasons. You've got alignment issues. The Retrieve 3D model might not perfectly match the scan geometry everywhere. The lighting in the original scan is usually uneven and unknown. Parts of objects are often occluded, hidden from view. The input images might be low res. And traditional methods to optimize PBR material parameters often involve complex, computationally expensive differentiable rendering.
It sounds like a minefield. How does Literality navigate it?
They have a pretty robust pipeline for this too. First, automatic crop mapping. They use SAM, the Segment Anything model from Meta AI, to automatically segment the input RGB images, pulling out meaningful patches corresponding to different material regions on an object. Then a multimodal large language model, an MLLM, semantically maps these 2D image patches to the corresponding parts on the 3D model mesh. Like this image patch is the fabric seat, this one is the wooden leg.
Okay, so it knows where the visual information from the scan should go on the 3D model.
Exactly. Then comes this semantic and visual guided material search. It uses both language and vision to find candidate materials from a database. Language helps refine the search, like find a worn leather material. Vision compares the appearance. They use CLIP embeddings to find materials visually similar to the extracted image patches. GPT-4 even helps check if the albedo map, the base color texture of a candidate material, is visually compatible with the patches.
So it's searching a material library using both text descriptions and visual similarity.
Yes, combining both gives better results. But here's the really clever part, the final optimization. Instead of trying to optimize all the complex PBR parameters, which is slow and prone to errors with bad lighting, they do a lightweight albedo-only optimization.
Albedo-only, so just the color and basic texture.
Primarily, yes. They take the best matching albedo map found during the search and then subtly adjust its overall color distribution to better match the color seen in the image patches from the scan. They do this adjustment in the CIE lab color space.
Why that color space specifically?
Because CI Lab is designed to approximate human visual perception, so adjustments made in lab space tend to look more natural and preserve the perceived colors better. The key benefit is that this adjusts the overall color tint and brightness to match the scan without destroying the high-frequency details of the texture, the patterns already present in the good quality albedo map they retrieved.
So it's a smart shortcut. Get a good base texture, then just tweak its color to match the real object, preserving the detail but matching the look. Much faster.
Much faster and much more robust to noisy input, exactly. It gives great results without the heavy computation.
Okay, that makes a ton of sense for efficiency. So layout done, objects retrieved, materials painted, we have all the components. What's a final step to bring it all together into one interactive scene?
That's the final stage, stage 4, procedural reconstruction. This is essentially the assembly process.
Putting it all together.
Right. It follows a logical construction sequence. First, it builds the room geometry, the walls, floor, ceiling based on the parsed layout. Then it adds the architectural elements like windows and doors into the walls. And finally, it places all the retrieved material painted objects into the room at their resolved positions and orientations from stage 1 and 2.
So building the virtual room block by block almost.
Pretty much. But the absolutely crucial part here, the step that enables all the interaction and simulation we talked about, is assigning rigid body properties to each object.
Rigid body properties, like in a game engine.
Exactly like in a game engine. They take the 3D mesh geometry of each object and use that to define its collision boundaries. They also assign physical properties potentially inferred from the object type or database mass, friction, stuff like that.
And that's what lets things bump into each other realistically.
That's what enables the physics engine to take over. So when the scene is loaded into a simulator or game engine, objects obey gravity. They collide realistically, you can pick them up and drop them. Articulated parts like doors can swing open based on physics constraints. It makes the digital replica truly dynamic and interactive, not just a static model.
Okay, the whole pipeline makes sense now. It's a really comprehensive approach. So, stepping back, what's the big picture impact? We have these detailed, interactive digital copies of real rooms. What does this unlock?
Well, the big contribution is really being the first system, as far as the authors claim, to go all the way from a room-level scan to a truly graphics-ready environment. That means combining a high visual realism with that interactive functionality, including articulation and physics. That combination is the novel part.
And the impact of having that capability.
It's pretty broad. We touched on it earlier, but now we can see why. For AR/VR, you can now scan your actual room and then interact with a highly realistic virtual version of it. Imagine redecorating your room in VR, trying out furniture that behaves realistically.
That would be cool.
For gaming, developers could potentially scan real locations or props and bring them into games as fully interactable objects, speeding up development and increasing realism.
Makes sense.
And it's huge for robotics and embodied AI. Instead of training robots in purely synthetic, often simplistic environments, you can train them in highly realistic, physics-accurate digital twins of the actual complex environments they'll operate in. The paper shows examples like simulating a robot arm interacting with objects in a scene reconstructed by Literality.
So better training data, basically.
Yeah, much better, much more realistic training data. And of course, digital twins in general for architecture, facility management, industrial design. Having a functional, interactive replica opens up way more possibilities than a static model. The paper actually shows some compelling examples. They show a scene being relit under different conditions. Morning light, TV glow, which works because of the PBR materials. They demonstrate physics interactions, like apples realistically scattering when dropped on a table, or a toy car colliding with furniture. And they show scene editing, swapping out objects easily because the whole scene is modular and object-centric, with physics ensuring things still sit realistically.
Those examples really drive home the graphics-ready aspect. It's not just a claim, they show it works. But this sounds almost too good to be true.
Yeah.
How do they actually measure its performance? How do they prove it's better than other methods? Hashtag benchmarking and performance.
Yeah, they did quite a bit of benchmarking. Since this specific end-to-end task didn't really have established benchmarks, they effectively created 3 new ones to evaluate different parts of their pipeline.
Okay, what did they measure?
First, retrieval similarity. How well does it find the right 3D model? They tested this on the ScanNet dataset, which has lots of scan scenes, and compared the models Literality retrieved against the huge ShapeNet database. They measured similarity using the L1 chamfer distance, which compares point clouds, and Literality significantly outperformed other methods like Scannotate and Digital Puzzle.
So the training-free hierarchical retrieval really works well.
It seems so, yes. Second, they benchmarked the object-centric PBR Material Estimation. They took 111 objects from 5 real-world iPhone scans, so challenging data, and compared the quality of the materials Literality generated against methods like Photoshape and Make It Real. They found Literality was more robust to the noise, the bad lighting, the misalignments you get in real scans, and quantitatively produced better PBR materials based on perceptual metrics.
That lightweight albedo optimization pays off then.
It appears so. And finally, they benchmarked the end-to-end graphics-ready reconstruction. This looks at the whole picture. They rendered images of the final scenes generated by Literality and compared them to the original photos from the scan. They used standard image quality metrics like RMSC and SSIM, but also, importantly, LPIPS.
LPIPS, why is that one important?
LPIPS stands for Learned Perceptual Image Patch Similarity. It's a metric designed to better capture how humans perceive visual similarity, rather than just pixel-level differences, so it's better at judging if something actually looks right. Across all these metrics, Literality significantly outperformed other comparable pipelines like Phone2Proc and variants of Digital Cousin.
So strong quantitative results across retrieval, materials, and the final scene quality. That's pretty convincing. But, as always in research, no system is perfect. What are the limitations they acknowledge? Where does it still struggle? #HEG limitations and future directions.
Right. They're quite upfront about the limitations. One is the reliance on curated asset databases and some hand-tuned rules for things like the scene graph relationships. This means it might struggle with really unusual room layouts or furniture that's completely unique and not in the database.
Makes sense. Dependency on the library.
Exactly. Also, the material estimation, while robust, mainly focuses on albedo. It doesn't fully capture complex lighting effects or detailed specular reflections. So the relighting works well, but maybe not under drastically different novel lighting conditions compared to the scan.
Okay, so limits to the relighting fidelity.
Minor limits, yeah. Another thing is it currently tends to miss or omit very small clutter objects like, mugs, books, cables scattered around. It focuses on the main furniture. Adding that clutter is important for full scene realism.
Little details.
Yep. And like any pipeline, it's sensitive to errors early on. If the initial object detection messes up badly, that error can propagate through the system. Lastly, their collision resolution method, while clever, is relatively simple and might struggle with extremely cluttered scenes, potentially leaving tiny overlaps between objects.
Okay, those seem like reasonable limitations for a first system tackling this.
Yeah.
So where do they see this going? What's the future work?
There are some exciting directions. Obviously, integrating detection and retrieval for those small clutter objects is a key next step for completeness.
Right. Adding the mugs and books.
Improving the material modeling is another big one. They want to move towards learning-based light estimation and recovering the full SVBRDF, that's the complex function, describing how light interacts with a surface from all angles. That would enable truly photorealistic relighting under any condition.
That sounds computationally intensive, though.
Potentially, yes, but that's the research frontier. They also want to explore more advanced collision resolution techniques, maybe using physics simulation more deeply or machine learning, to handle really complex object arrangements perfectly.
And scaling up.
Absolutely. Scaling from single rooms, which is the current focus, to handling multi-room apartments, entire houses, or even whole buildings. That opens the door to large-scale digital twins for architecture, urban planning, and more.
Wow. It really feels like we've gone from just capturing a scene's appearance to capturing its essence, its structure, its materials, its potential for interaction, from a static 3D photo to a dynamic, functional digital twin.
That's a great way to put it. It bridges that gap between just seeing a virtual replica and being able to truly use it, simulate it, interact with it.
So final thought for our listeners. Think about this. Imagine you could walk into any space, scan it quickly with your phone, and instantly have this editable, interactive, physically accurate virtual version. Your home, your office, maybe a historical site. What could you do with that kind of capability? What new experiences, tools, or insights does that enable?
It really opens up a fascinating range of possibilities for design, training, collaboration, preservation, so many areas.
Definitely something to ponder. We highly recommend checking out the Literality paper if you want to dive even deeper. Thanks for joining us on this deep dive at AI Paper Podcasts.